Good afternoon, everyone. Today we'll discuss about applications of Fermi-Dirac distribution law. So here we'll go with one of the important application of Fermi-Dirac distribution law, that it is applied to explain the behavior of electrons in metal. So before coming to the Fermi-Dirac distribution law of energy of electrons in metals, let us discuss about free electron gas. That means because we are here dealing with explaining the Fermi-Dirac distribution law being applied on to explain the behavior of free electron gas. That means what is free? Free means whenever no forces acting on the system, which means no interactions among the electrons and the ions in the metal. Second one, no interactions among the electrons themselves. That means the electrons which are moving around the positive ions are free to roam around. Means the motion of an individual electron is not affected by the another individual electron. That means they are free to roam around the positive ions in metal. Second one is electron, and this is basically a half spin particle being fermion in nature, and it always obeys Pauli's exclusion principle. So you know that it is represented by E negative. And third thing is gas. We all know what is gas. That means in which the motion of molecule is there. And similarly here, these molecules travel freely inside the metal. What are these molecules? These are basically electrons. That means only the difference in the electron gas and the simple gas is that the constituent particles of the gas here are electrons, which are charged particles, and whereas in case of a simple gas the constituent particles are molecules. All right, this is all about the free electron gas. Now we'll discuss that how do we apply Fermi-Dirac distribution law to explain the behavior of this electron gas in the metal. See here, this is the presentation of a metal in which there are positive ions which are fixed in nature, and the negative electrons are roaming around these positive ions, and the behavior of these electrons are independent of each other. And see here, this assembly of electrons in metal is basically called as free electron gas. And we know that electrons being fermions obey Fermi-Dirac statistics. And as per Fermi-Dirac statistics, the number of electrons having energy range between U and U plus du is given by Nu du. Alright, you know that. How do we write it? As it will be Nu du is equal to Gu du divided by e raised to the power alpha e raised to the power u upon kt plus 1. Let us consider this as equation number 1. Now let us come to Fermi energy. We know that fermions obey Pauli's exclusion principle. Here we are talking about electrons, means we are dealing with the behavior of electrons in the metal. Alright, although there are other members in the family of fermions, whereas they are like neutrons and protons, but here we are talking about electrons only. In this case, two fermions cannot occupy the same quantum state. When we start filling the empty system with electrons, that means the electron first enters into the lowest energy level, then to the first, then to the second, and so on to the highest energy level. All right, see here, this is the sequence in which we fill the electrons and the electron occupy a particular energy level. See here, this is the case in which two electrons are lying in the same state. That means this kind of a state is not acceptable because it is not obeying the Pauli's exclusion principle, that no two fermions can occupy same quantum state. Next we have the situation of this type. That means we see here, when we go on filling the electrons in the empty system, first electron occupies the lowest energy level and rest of the electrons consecutively fill up the highest energy level, and this level is known as the highest energy level in which the electron is residing, and this level basically is known as Fermi energy level. That means the highest filled energy level in the system is called as Fermi energy level, and the energy occupied by that electron in this energy state is called as Fermi energy. See here, at absolute uh, 0 Kelvin temperature, the kinetic energy of the electron occupies the highest energy state, which is known as Fermi energy. Alright, the energy here is represented by UF. I hope now we'll apply the Fermi-Dirac distribution law to explain this Fermi energy level of the electrons. Now, Fermi energy UF in terms of parameter alpha and temperature. See here, the occupation index, we know that, is represented by number of particles and number of states, whereas number of particles are represented by Nu and the number of states are represented by Gu. At temperature is equal to 0 Kelvin and energy greater than Fermi energy level, that means UF, this condition is represented by basically this state, alright, because energy here is, energy of this state is greater than as compared to energy of the Fermi energy level. That means in that case all the states are empty and the number of particles are 0. So the occupation index comes out to be equal to 0. That means there is no matter of applying the Fermi-Dirac distribution law on this state. After that, at temperature T is equal to 0 Kelvin and energy either equal to or less than Fermi energy is represented by these states. Alright, see here, for each state Nu is equal to 1 because the Pauli's exclusion principle is taken into the consideration. That means number of particles in every state is equals to 1. So the occupation index here comes out as Nu upon Gu is equal to 1. We can also explain the process by taking the graph between occupation index and the energy. See here, when we plot a graph between Nu, Gu and energy of the system, we'll get a graph of this kind. See here, when the temperature is equal to 0 Kelvin, that means we get this type of a graph. That means here in this level the occupation index is 1, and whereas this energy basically represent the Fermi energy UF. Alright, when we keep on or when we go on increasing the value of temperature greater than 0 Kelvin, the graph falls like this. That means the for temperature greater than 0 Kelvin, no sharp cut off as it is in the case of temperature T is equal to 0 Kelvin. So the occupation index go on decreasing with increasing the energy, right? And we know that naturally the occupation index will go on increasing as we go to the higher energy level. Above the Fermi energy level, the number of particles are not lying over there. Alright, so by the definition of Fermi energy level, occupation index is 1 and the energy for that level is UF, and this whole the process is at the temperature of T is equal to 0 Kelvin. After that, from equation number 1, this was the equation number 1, Nu, if we take Gu toward this side, that means we'll get Nu upon Gu is equal to 1 upon e raised to the power alpha, e raised to the power u upon kt plus 1, which will be equal to 1 because occupation index in the Fermi energy level is always equal to 1. So cross multiplying and solving this, we'll get e raised to the power alpha plus u f divided by kt is equal to 0 because energy of this state is UF, and simplifying because it will be exponential raised to the power 0. When we compare the powers, we'll get alpha plus uf upon kt is equal to 0, and alpha comes out to be is equal to minus of uf upon kt. Let us consider this as equation number 3. We can substitute this value of alpha over equation number 1. So we get nu du is equal to gu du divided by u minus uf upon kt plus 1. So considering this equation as equation number 4. Here we know that nu du represent the number of particles or number of electron distributed in terms of energy, whereas gu du is the phase space, alright, in terms of energy. So number of phase space cells in momentum interval p to p plus dp, we know that it is gp dp is equal to gs4 pi vp square upon hq multiplied by dp. You know that from where we have got this equation. Here gs is equal to 2s1, which is known as the spin degeneracy factor due to spin of electron, and we know that spin of the electron is always half. Further, when we substitute the spin of the electron in spin degeneracy, we'll get 2 into 1 upon 2 plus 1, which comes out to be equal to 2. Substitute the value of gs in the equation. That means we'll get gp dp is equal to 8 pi vp square upon hq multiplied by dp. This is the value of phase space cell in terms of momentum. Now we need to convert this momentum in terms of energy, because we are here interested in deriving the expression for Fermi-Dirac distribution law in terms of energy. So here we know that the relationship between momentum and energy, u is equal to p square upon 2m. We can write p square is equal to 2mu or p can be written as under root of 2mu. Let us differentiate this equation. We'll get 2p dp is equal to 2m du, and dp can be written as m upon p multiplied by du, whereas p can be replaced as under root of 2mu by writing it as is equal to under root of m upon 2u multiplied by du. That means we can now replace our n p dp in terms of nu du by replacing the value of momentum as under root of 2mu, whereas by replacing the dp as under root of m upon 2u multiplied by du. See here, now number of cells in the energy range u to u plus du becomes gu du is equal to 8 pi v upon hq. Alright, this was the basic expression. Alright, I have substituted the value of gu du, and also I have substituted it in terms of energy. That means we'll get, because here we had p square, that means p square is 2mu. Here we have dp, that means dp is nothing but it is under root of m upon 2u multiplied by du. By simplifying this, we'll get this kind of expression. Now using this equation in equation number 4, this is basically a equation number 4. Now substitute the value of gu du over here. When I substitute the values of gu du, I'll get nu du is equal to 8 under root 2 pi v m raised to the power 3 upon 2 divided by h raised to the power 3 multiplied by u raised to the power 1 upon 2 divided by e raised to the power u minus uf divided by kt plus 1, which is basically a final expression for Fermi-Dirac distribution law of energy among free electrons in a metal, and this explains the distribution of electrons in terms of energy. So this was all about the derivation of Fermi-Dirac distribution law. Now let us come to the term Fermi energy value. That means it is the derivation of energy of the electron possessed by the highest energy level or Fermi energy level. At 0 Kelvin, the number of energy states occupied by the electron for energy state from 0 to EF is equal to number of electrons. Naturally, the total number of electrons are calculated by integrating the number of electrons in terms of energy from lowest energy level to the highest energy level, and the highest energy level is represented by EF. Here it is one and same thing. Either you write the value of Fermi energy as EF, and you can write it as UF, and the energy of the total system is either represented by E or U. So it is one and same thing. Either you write all the terms in terms of U, and either you write all the terms in terms of E. So here you can see that it is the integration of 0 to EF, and it is the factor which is NEDE. See here, the exponential term here is taken as 1. You know that when we talk about at temperature is equal to 0 Kelvin or at absolute temperature, 1 upon e raised to the power alpha, e raised to the power u upon kT plus 1 is equal to 1, because the occupation index is 1 at temperature T is equal to 0 Kelvin. That means we can take this factor as is equal to 1. So finally we are left with this kind of equation. Taking all the constants out, inside we are left with integration from 0 to EF, e raised to the power 1 upon 2 dE. Integrate it and substitute the lower upper and the lower limit. We'll get the expression of this kind, but here we are interested to calculate the value of EF. Take this EF toward that side, we'll get the expression as, and taking the cube of the under root, we'll get EF is equal to h raised to the power 2 divided by 2m multiplied by 3n upon 8 pi v raised to the power 2 upon 3. Here it is clear now that the Fermi energy value depend upon the mass of the electron and density of the electron, because density of the electron is represented by n upon v, number of electrons per unit volume. So sometime the question is like, prove that energy possessed by the electron in the Fermi energy level depend upon the mass of the electron and density of the electron. So I hope now it is clear. Sometimes the numerical problems are generally asked on this Fermi energy value. Alright, we know all the constants here. We know the mass of the electron, but what we only require to evaluate the value of EF is only the density of the electron. That means number of electrons per unit volume. If we know, we can calculate the value of EF. So this was all about the Fermi energy level, electron gas, and application of Fermi-Dirac statistics to explain the behavior of electrons in the metal, and after that evaluation of that Fermi energy value. So I hope it is all clear. And still, if you have any problem, you are most welcome to let me know. This was all for the day. Thank you and have a nice day.